Now, what if you, how much energy are you going to need if you want to double the amplitude? Okay, well, let's show that that's true. Not everybody got that. Lots of folks said just 2. Okay, so if E is proportional to A squared, where E is the energy and A is the amplitude, this was in the lecture on intensity, then how much energy do you need when you have twice the amplitude? So the energy then, proportional to the 2A squared. 2 squared is 4. So this would be 4A squared. So 4 times what it would have been for the amplitude for a single amplitude. Okay, questions? Okay. Question 68. How to do question 68, you needed to know about fixed and free boundaries. Okay, so in each of the 4 waves, the pulse on the left is the original pulse moving toward the right. The center pulse is the reflected pulse, and the pulse on the right is a transmitted pulse. Describe the rigidity of the boundaries at A, B, C, and D. In other words, I wanted to know if it was fixed or free, or hard or soft. Okay? So, by definition, a fixed boundary has an inverted reflected wave. Why? Because as the wave pulse comes in, it's going to try to push up on that point, and since it's held steady, okay, Newton's third law says to every action there's an equal and opposite reaction, and so the wall is going to push down, so it pushes down, so the reflected wave is the inverse of the incoming wave. In other words, the polarities are opposite to each other. And sure enough, if you look at the reflected wave at A, you'll see that this is true, and therefore this is a fixed boundary. Okay, for a free boundary, the reflected wave has the same polarity. That means that if it's up, then the reflected wave is also up. And we saw that when we looked at the animation, right? As the wave came in, right, it went up, and so it came back the same way. All right. So if you look at B, the incident wave goes up, the reflected wave goes up, and therefore this is a free boundary. Okay. C, you had an incident wave that was below the reference line. The reflected wave is also below the reference line, and therefore this is a free boundary. For D, you had the incident wave was down, the reflected wave was up, and that made this a fixed boundary. The other nomenclature was hard, soft, soft, hard. I didn't care which one you used. I used either one. Something good happening? Yeah, okay. I figured. Okay. 24. Any questions about 68? Okay, 24.
24.
Okay. Okay. 24. I'm looking at a spring, and I see this going on the spring. Okay? Okay, so which way are the particles moving?
Up and down.
Up and down. The particles are moving up and down. All right, you're seeing this. Okay, so particle movement is
Just guess.
up and down. This is the particles. Now the wave motion is to the right. So we know that the particle motion and the wave motion are perpendicular to each other. What kind of wave is this? Transverse wave. This is a transverse wave. Okay, so what does a longitudinal wave look like? Okay, a longitudinal wave is this one. Right? So it goes back and forth. Right? Longitudinal wave. So, yes, expansion, compression, etc. Which way do the particles move? The particles move back and forth this way. Okay, and the wave also moves in the same direction. They move parallel to each other. This is a longitudinal wave. Okay, guys.